Now it's starting. Okay. Yeah, I'm very happy to give this talk here today and give you a small introduction into chemometrics, and also one approach that we developed for the analysis of complex data. And I think also Marina gave a very good introduction how this complex data can be generated, and I will show you now what we can do with this data, how we can analyze this data. Yeah, in general, there's a lot of different approaches that generate complex data. And of course, one very important step is to get information out of this data that you are aiming at. For example, for food profiling, this is of course a very important step for this approach. Yeah, the aim of this data analysis is to classify the samples. This is what Marina already also showed you. But other important aims are to characterize the samples and to identify markers. This is also one part that already was shown. And of course, also for the characterization and the identification of markers, chemometric approaches should be applied on the data. So the field of tools that is relevant here is called multivariate approaches, because many variables should be analyzed simultaneously. And this is why these approaches are called like this. And there are two different types of approaches for this task. One is the unsupervised approaches. They're also called data mining approaches. And the other one is the supervised approaches. And I will shortly introduce both of these approaches, and I will show you an approach that we developed that is based on machine learning. So unsupervised approaches are also, which is also called data mining or explorative approaches. The idea behind these methods is that data is analyzed without further inclusion of information about classes, for example. And the aim here is pattern recognition. So the samples should be analyzed, and patterns for different classes, for example, should be found. But the main thing is that no pre-information about this is given. So there are different approaches. The first class, or there's the first class of approaches, which is called cluster analysis. Here, distances between the different samples based on the different variables are calculated, and the cluster algorithm then gives it the result of different groups of samples, which are called clusters. The other approach is principal component analysis. Is applied very often in chemometrics, and the idea here is that linear combinations of the variables are built, and new principal components are obtained. And these principal components are built to reduce the dimensions. You have data with a lot of different variables, and the idea here is to reduce these dimensions to very few variables that contain the main variance, so the main differences that hopefully you're interested in, and that can be analyzed in an easy way. On the right side here, you see an example based on simulated data. So if you have a metabolomics analysis here with a lot of different features, then principal component analysis would build one principal component here that can separate very nicely between two different groups. And this is done based on the scores. This is one parameter of the principal components. This is the coordinates of the new build components. And the other parameter is called the loadings. And the loadings are the connections between these old variables and the new principal components. So the loadings can be used to evaluate which variables are mainly influencing the principal components. And in the best case, this is also the components that you're interested in to separate different groups. However, this is of course not always the case, that the biggest variances in the data are the ones that you're interested in. Often there's other variances that are not the ones that build the classes that you are looking for, and in this cases, supervised approaches should be applied, and this is also called machine learning. This means that you build a model that is based on the specific variances of the groups that you are interested in. For example, if we have this asparagus data set, the groups would be asparagus samples from different countries like Germany or Poland or Peru. In this case, you need additional data, because if you focus your model on these differences, you have to make sure that these differences that your model is focused on are really the class differences and are not sample specific. For example, this could be noise in the data or other variances that are not really specific for the classes that you are aiming at. So this is why you need more data with which you can make sure that your model is really working as it should. There are different machine learning approaches. For example, neural networks, they're quite common in a lot of different fields, but there's also random forest and support vector machines. They're more common in the chemical analysis because they don't need so much samples as neural networks. And in many cases, you don't have as many samples as we would need here. One negative part of this machine learning approaches is that they are often applied as black boxes. And this means that you just put your data in and you get the result, meaning, for example, the assignment to the group of German asparagus, but you don't know what's really happening inside this model. And of course, this is very dangerous. And of course, it should be the aim to also know why the classes are assigned. And there's a lot of very nice examples for why you should know what your model is doing. I show you here one of these examples, and this is a model which is based on image data, and this is trained to identify cows or to identify what animals you have. And you see here on the left side that this picture is classified pretty well as a cow. But you also see that if you have a cow in a different setting than you would maybe expect, like with the green grass in the mountains, it would be maybe a setting where you accept the cow. But if you have it in the ocean here or at the beach, then this model has problems to find out that this is a cow. And the reason here is that obviously the model needs grass in the background to know that it is a cow. And of course, this is not how the model should work, because it shouldn't be dependent on that there's a cow and not what the background is. So this is, I think, a very nice example that you should know what your machine learning models are using to classify your data. I use random forest a lot because random forest has a lot of examples, a lot of advantages. Random forest is called random forest because it is based on multiple decision trees. This is what you can see here. And one of the advantages is that random forest has an internal validation. I will show you on the next slide why or how this is working. Another advantage is that it has no distributional assumptions. This means that you don't need normally distributed data for this approach to work. I think this is also a very nice advantage. It is also very flexible regarding input variables and output variables. This means that you can use quantitative and qualitative data. You can make classification and regression models and even other models that are relevant in medical area. It is also very nice if you have high dimensional data, and this means that you have a lot of different variables and not many samples. And this is, I think, often the case when you have analytical data. For us, also very important is that you have efficient implementations, meaning that you have an implementation that is quite fast, and we have this here. And there's also a lot of different approaches for variable selection, so this would be an important step. to open the black box and to know what this approach is doing. Yes, so random forest, as I said, is based on multiple decision trees. For each of these decision trees, a bootstrap sample is used to build the tree, and this means that a subset of the samples that uses them once or more times than once. And the very big advantage is that we have samples here that are not used for the training process for each tree, and these samples can later on be used to validate the single tree and the whole random forest also, because then only the trees are used that don't use these samples for training. And so we don't need additional validation data, which is a big advantage. The other random effect of random forest is based on the different splits of the decision trees, because at each split, a random subset of the variables is used as candidate variables, and for each of these variables, the optimal split variable and optimal split is determined. And this enables that you have different decision trees. So as I said, random forest can also be applied to evaluate the variable importance. And this is done individually for each variable. And one importance measure that is often applied here is called permutation importance. This means that you just shuffle randomly the values of a variable over the samples, and then you test you train a random forest based on you test the random forest based on the shuffled data set for this one variable and based on the original data set, and then you compare the performance of those two models. And if the difference is very big, then your variable is very important, and if the difference is not very big, then this variable is not very important. So this is the general idea behind it, and there's quite a few different selection approaches that use this importance measure to separate important from non-important variables, and they use statistical tests to generate this threshold. We compared some of these approaches in a comparison study that you can see here, and we found out that those two approaches here are the top performing ones. So there are different aims for variable selection. The one that is often applied or that is often important is to generate parsimonious models. This means that you want to have a minimal set of variables, and this means that redundant variables should not be included in your set of variables. In this case, it makes sense to use this permutation importance, and you can generate quite nice results. However, our idea is that we want to open the black box, as I said before, that we want to know what is happening inside the machine learning models. And in this case, this means that we want to get information about the underlying mechanisms. And this means that we are interested in all variables that are relevant for this classification model. And this means that we want to include redundant variables. And in this case, the permutation importance is not the best choice. And this is why we were thinking about an alternative approach that includes this redundant variables and that also includes relations of variables into this importance measure. And this is why we wanted to build an importance measure based on tree structures. This importance measure is based on two different existing techniques. The first one is called surrogate splits, and this is developed for random forest to deal with data that has missing values. This happens in the medical area quite often, that you have samples that have missing values. And this, of course, you still want to apply your machine learning models or your machine learning techniques, even if you have missing values. And the idea here is that in the training process of the random forest, you not only determine primary splits and primary split variables for each of these splits here, but you also determine surrogate splits that can replace this original split as good as possible. And if you have a sample like sample 5 here that has a missing value, then it's not a problem to use this random forest or this decision tree here, because in this case, when this variable is used that is missing, then you can just use the alternative variable, which is called surrogate variable. The second idea that our approach is based on is called minimal depth. And this is an importance measure that is based on the structure of the trees, as I said. And this just has a look at the decision trees and evaluates at which position the variables appear first in this decision trees. For example, variable x8 appears first here. So it has a depth of 0, which is quite important. And this is done for all of the trees and all of the variables. And the minimal depth is averaged over all of the trees. However, this means that low values are important. This is different than other importance measures where high values are important, but nevertheless, it's also a score for the importance of the variables. Our approach combines those two ideas. This means that minimal depth is applied not only to the primary split variables, but also to the surrogate splits. In this case, it means that variable x2 has a surrogate minimal depth of 0, and it would have a minimal depth of 3 because it didn't appear here, but surrogate minimal depth is 2. And this has the advantage that also relations of the different variables are included in our importance measure. Interesting for the relation analysis is also how these surrogate variables are determined. And this you can see in this slide here. There the agreement is determined, and this means, for example, you have a split here that has 6 yellow samples and 4 blue samples, and it perfectly splits those samples in these two classes. For this, you are looking now for an alternative when this variable is missing. A surrogate split could be variable x2 that does 2 of the samples in the wrong direction, and this means it has an agreement of 80% or 0.8. In the original implementation of random forest, there was another alternative that you can use when data is missing, and this is called the majority rule. And this just means that samples are sent in the direction where most of the samples go. So in this case, it would be this direction where 6 yellow samples are going. And in this case, you would still have 60% right. And of course, a surrogate split should be better than the majority rule. And this is why another parameter is introduced, which is called adjusted agreement, that just compares this surrogate split performance to the majority rule and sets the performance as 0. And in this case, you see that this is at 0, and this means that adjusted agreement is 0.5. So we want to analyze variable relations, and this adjusted agreement is a very nice score that tells us how those variables are similar in our classification model. So what we do now is that when we want to analyze the relation between or the mutual impact of these two variables on the model, we just have a look at one variable, x4, for example, have a look at all of the splits that are based on this variable, and then we read the adjusted agreement from this variable that we're interested in. We calculate the average over the whole random forest, and we get a measure of a relation parameter that shows us how these two variables are related to each other, or how their mutual impact on the classification model is. So in computer science, the first step often when you develop a new approach is that you generate a simple simulation study to see how your new approach is performing. And this is what we also did here. So we simulated data, 50 replicates of 100 samples. And we developed, or we simulated 3 causal variables that determine the outcome, also 3 variables that also determine the outcome, and a lot of variables that are non-related to this outcome. In addition, we also simulated correlated variables, 10 that have a very high correlation, 10 with a medium correlation, and 10 with a low correlation. And we simulated those correlated variables for those causal variables here and also for those 3 non-causal variables. So we have different types of variables in our data set. We have a block of causal correlated variables, a block of causal non-correlated variables, one of non-causal correlated variables, and a whole bunch of non-causal non-correlated variables. Those were simulated because we wanted to generate a high-dimensional setting where there's more variables than samples. So here you can see the performance of minimal depth and surrogate minimal depth. To remind you, low values mean important variables, and you can see here that this variable that has high correlations or has highly correlated variables here is selected not even in 50% of the cases, because those variables can be replaced by the correlated variables in the decision trees, and this leads to lower importance scores, or to higher importance scores that mean lower importance. In the surrogate minimal depth, you see the different effect, because here the variables with high correlated variables show lower importance scores. So to sum up, you can see that here a lot of more of the really causal variables are selected based on this threshold that you can see here. We also had a look at the relation that is based on this mean adjusted agreement parameter that I just showed you. And we also saw here that the correlations can be reproduced by our approach. So the variables that are correlated to variable x1 are selected. And here still, and with the low correlations, we select approximately 30% of the variables. And the same happens for the non-causal variables here, because we don't have very much causal variables in the model. I think if we would have more, then this would be not the case, because then these variables would not be present in the decision trees as much as they are here. Yeah, so you can see that we can reproduce the correlations here, but the interesting thing about our relation parameter here is that not only the correlation is important for this mean adjusted agreement, but also the mutual impact of these variables in the classification model. And this means also the relation to the outcome that we're interested in. Outcome, for example, the different classes that we want to separate in our model. Yeah, we also did some more complicated realistic simulations. I will not go into the detail too much now, but here we also compared our approach with the established ones that we found as to be very good performing. And we found out that if we choose our parameter S, meaning how many surrogate variables are determined for each split, then this approach is even a little bit better than these approaches that are established. So including relations in this selection process improves the selection of important variables. Yeah, now I can come back to what you already heard from Marina, because we did this application of this approach to the data that you already know, because this is the data from the Aspargas analysis. Here, the aim was to separate those samples according to the origin of the Aspargas samples. You can see here the different countries. And our aim here was to not only have this classification results, but to have a look into what is happening inside the model. So how are the different variables interacting, their mutual impact on this model. So you can see here, this is a heat map, and this is the relations that we calculated based on our mean adjusted agreement. And you can see that based on this mean adjusted agreement, we can determine different clusters of variables that contain similar information for the classification. And this is what you can see here. here we here are two metabolites for each cluster are shown, and you see that similar information for the classification are contained in this variable. So we can find out the clusters, or we can find out the metabolites that have a mutual impact on the model. As an example, you can also see here that cluster 4 contained different phytosterol esters, stigmasterol ester and episterol ester, but also some more. And the interesting thing is that they're all related, or that they're all interacting also in a biological pathway. And this is the sterol biosynthesis pathway. And so we could also find relations, or find this mutual impact of variables that are interacting also biologically in a pathway. So we could identify a relevant pathway for the separation of the different origins of the Aspargus samples. Yeah, so I'm at the end of my talk. I showed you possibilities how complex analytical data can be analyzed. There are supervised and unsupervised approaches. When you apply supervised approaches, I think it is important to have a look at what your model is doing. And we developed an approach that includes relations in the selection process of important variables. And this approach can be applied to select important variables, but also to analyze the mutual impact of variables on the classification model. We already applied this approach in different areas. In food profiling for Aspargus samples, I just showed you, but we also applied it to data from different vibrational spectroscopy experiments. Here on an NER data to separate different origins of hazelnut, but also to surface enhanced Raman scattering data. And also for this kind of data, this approach is very promising, because here we have data from a lot of different molecules that are superimposed. And this approach can help to find out which molecules are interacting, which are co-occurring in the different spectra. And there, this relation analysis is very helpful. So here we could, for example, see the interaction of lipids with drugs in living cells by the application of surface enhanced Raman scattering and this novel approach. So yeah, I'm at the end of my talk. Thank you very much for listening. And if you're interested in this approach, you can find it at the GitHub page here. I have to thank Silke and Sven, who were involved in the development of the SND approach, and also Sören, who did the food profiling analysis.
Hey, Stephan.